to talk to you about the kidneys and their amazing function and how they help us reabsorb water and nutrients and keep us alive. So we're going to start up top right here. And this is just kind of, it's not an anatomical diagram, but a diagram kind of discussing what's going on. So we have 4 different steps. So in our little drawing, we've got the kidney, we've got our blood vessels going around. And so we have blood going down and then in. And our first step is going to be filtration, and this is 20%. So this is taking into consideration size, charge, and pressure. And then we have number 2, we have all of these outlets right here, and that's reabsorption, and that's specific to the different, what's the word I'm looking for? Metabolites. Step 3 is secretion, so we're intaking things into the kidney. And then this area right here is hormonal control. And this is going to be where step 4 takes place, and that's excretion. And by the time we're done, this is symbolizing the bladder. We have about 1.8 liters that make it out of our body. So 2 things to remember is salt always follows water. And the second thing is PAH makes penicillin go around again. So when they discovered penicillin and made penicillin, it was filtered through the kidney quite fast, too fast for what the supply and demand was. And so they paired it with PAH to make sure that it would keep cycling through the kidney and doing its job so that less could go further. Okay, so now we're gonna skip down here, and this is going a little bit more in depth into the filtration. So this is the glomerulus, and we have our efferent and our afferent side. And then this bunch of X's on all of these symbolizes the basement layer, and that's 12 to 25 nanometers, and this is negatively charged. And then we have podocytes lining these, and that's 5 to 12 nanometers. And we also have our glycocalyx lining that right there. And then our endothelial cells are right here. And we've got lots of these different podocytes going up and down and making sure that everything's all connected. So, and then what we've got in here is our metabolites. So none of these are proteins. It's H2O, glucose, potassium, calcium, sodium, chloride, and lactate. They're all taking place there. So before we go any further, let's talk just a little bit about the basic anatomy. So we've got our bladder and our urethra, we've got our ureter leading up to the kidney, and then you have your cortex and your medulla. And this is where all the magic's happening, is your medulla, where we have all these nephrons. So now we're going to go into the nephrons and the 2 different types and all of the amazing stuff that happens here. So our first one is the cortical nephron, and then we have our juxtamedullary nephron. And these both connect at the collecting tubule. So here are the different parts. So first of all, you have Bowman's capsule in both of these. And inside Bowman's capsule, you have your glomerulus. And the glomerulus is a bunch of blood vessels that are bunched up together, and then they split and they come out. So you have your, this is probably going to be a better place to show you. You have your afferent arteriole, which is coming out this direction. So this would be your afferent arteriole on this side. And then you have your efferent arteriole coming out this other way, going up and around the top of that distal tubule. So continuing with kind of the blood and what's going on, it comes and it wraps around all these different areas. And then you've got your, it comes down and through both sides. This is symbolizing the cortex is this larger section up here. And then down here is the medulla and the outer, and then you have your inner medulla, which is this section down here. So the vasa recta is another big grouping of the blood vessels, but that only takes place in the juxtamedullary nephron. And then you have your peritubular capillaries, which are running back and forth right there. So anyways, okay, moving on, we have our loop of Henle, and they both have a loop of Henle. And then you have, well, let's start at the glomerulus actually. Coming off of that Bowman's capsule, you have your descending tubule, and then you have your loop of Henle, and then you have your ascending tubule, and then your distal tubule. So on this side, you've got your descending, loop of Henle, ascending, distal, and then they connect at the collecting tubule. Another important thing is this little grouping of cells right here across from the glomerulus Bowman's capsule apparatus is called the macula densa, and it contains the macula densa cells. And we'll talk a little bit about what they do, but they are specifically there to sample the filtrate and make sure that the right things are being absorbed at the right rates. Okay, so in correlation to our 1, 2, 3, and 4 that we talked about a little bit earlier, filtration is where, or the Bowman's capsule, glomerulus, is where we have filtration happening. And then in the descending and ascending tubules, we have reabsorption and secretion taking place. And then excretion is 4. That's the collecting tubule. And then those drain into the ureter and then out your body from there through your bladder and your urethra. So a few more things about this. Cortical nephrons make up 90% of the nephrons in the kidney, and these have 2 capillary beds, and then the juxtamedullary make up 10%. That's 3 capillary beds. So let's kind of jump and go more in depth on each one of these sections. So the proximal tubule that comes right off Bowman's capsule, these are the cells we're going to be talking about, and this is where 70% of sodium is reabsorbed. So we've got our cells, and then anyways, we have our peritubular capillary coming through right there. So as you can see, we've got glucose coming in, we've got sodium coming in, you have amino acids coming in, and also more sodium, and then that kicks lactate out. And you have these aquaporins that allow H2O to go through. We have another pump right here that's a sodium-potassium pump, as well as right there, and those are driven by ATP, don't forget. And then we have glucose being pushed out of there. 70% of calcium and potassium are driven by the sodium coming through, and that's called solvent drag. And a couple helpful hints: low sodium concentrations in the cell lead to high driving force. And then 100% of glucose gets absorbed in proximal convoluted tubules. So if this is broken, if you're getting any glucose in the urine, that's a sign of diabetes and that this is broken and that you've pushed too much through there and now it's leaking into your urine. Okay, so little side tangent. This is a graph describing the tubular fluid to plasma ratio. So in your proximal tubule, it's kind of outlining that on the bottom axis, and then this one is the TFP ratio, and that's A is chlorine. Okay, let's jump down to this down here. Once again, we got our cells. So this is talking about carbonic anhydrase. And this is helping with our buffer system. So as you can see, we've got HCO3 being driven out in the same direction as sodium. And then we have another pump over here. Sodium's driven in, hydrogen's pumped out. Now, what happens is HLO3 comes and it kicks off a water and hydrogens, and then it leaves the CO3. excuse me, I think this is supposed to be CO3. Anyways, comes into the cell and then it adds to more water, and then this turns into HCO3, and you add a hydrogen in to get that, and then that goes to our buffer system that we're going to talk about in a second. Okay, next, straight proximal tubule. You have a pump pumping hydrogen in, hydrogen out, sodium in, and then you have a pump that is pumping out anions or hydrogen, and it's pumping in chloride. And this GH plus leads to anions, and then that chlorine that's pumped in gets pumped out right here. And CFRT is the loss of that protein, this GH plus. And so this leads to, this protein, CFTR. So when you lose that protein, you have cystic fibrosis. We're going to jump to the descending tubule now, and this is where most of the water is absorbed. So our levels were going from an osmolarity of 300 to 400, 500 to 600, and then it goes all the way down to 1200 for the juxtamedullary, and we'll go into more detail on that in the next video. But we've got different ways that water can move in and out, and so we have our aquaporins, and then we have between our cells. Next is our ascending tubule, and that there's channels that allow sodium, potassium, and 2-chloride in at the same time, and then we have 3 sodium that are pumped out, 2 pumped back in, just our basic sodium potassium pump, and then that chlorine is pumped back out over here, and so is that potassium. And then in between it, in all these others, we've had space for things to pass in and out over here, but for our ascending, it is now blocked off, so no water permeability right there. So 10% water just bounces back out. So that leads us to part of that ascending is we have our macula densa cells that we were talking about earlier that sample filtrate, and this has got a sodium chlorine pump that pump both in, so that's going from 150 to 100 to 75. And lastly, we have our collecting tubule, and this has got some special things to it. So we have our aquaporins. We are allowing sodium to enter the cell, and we are kicking potassium out. And this is also not water permeable, and that's another area that we're kicking potassium out. We have our sodium potassium pump, but we also have aldosterone on here. And we also have a G protein. So then we have antidiuretics that come in and they bind to that G protein, and these can be ADH or vasopressin, kicking that off and starting up the process. So we two special things that we need to remember: potassium and hydrogen follow each other, and hydrogen follows charge. So that's going to drive a lot of this. Okay, to the next video. Okay, and we're back for the second part of our first video. So we've got to talk about pressures and what is driving the pressures in this nephron system, or the glomerulus, and everything that's going on here, because as we know with pretty well everything in the body, it's driven by pressures and what's going on with our blood. So let's get started. Okay, so we've got our afferent arterial on this side and our efferent arterial on this other side, and 30 BCOP is what's going on in our glomerulus, and then we've got 15 capsule pressure, and then 55 for the HP. Now this one is very important that it's higher than the others to drive that force. Fluctuation in this is not good, and that is going to be caused by vasodilation and vasoconstriction. Whenever you vasodilate or constrict the efferent arteriole, that's only in cases of pretty bad dehydration. So you've got these macula densa cells that we talked about earlier that are going to sample the solution. They're specifically sampling for sodium chloride, and if that's higher, that's gonna equal a higher pressure. And when you have a higher pressure here, that is going to stimulate adenosine release, and then the adenosine comes in and says, hey, vasoconstrict, and that vasoconstriction causes a decrease in GFR, which we started with the high one, and so it's a feedback system. And this is known as the glomerular filtration rate. So we're going to jump up here. Two more things that are kind of important with this section is mesangial cells and podocytes are what give this strength, and the kidneys don't have lymphatic vessels in their cortex, so there's nothing to pick up if something's leaking. There's no maid here, and so we've got to make sure that these pressures are exactly where they need to be, or we're going to have some serious problems. Okay, so now we got to talk about how glomerular filtration rate and clearance are related to each other. And clearance is how quickly can I clear out X, or the solute, in milliliters per minute. So this is determined by Vx times V divided by P. And these are all in, well, I guess it's millimeters per milliliter per minute, and milligrams per milliliter. Anyways, we have to make three assumptions though with this in order for this to work. So the first one is there's no reabsorption of X. So if you've got to clear it out, it can't be reabsorbed. And then it has to be freely filtered. So X has to be something that's neutral. It can't have a positive or negative charge. And there's no secretion of this. So this is just something that passes straight through. It's not stopping to stay. Inulin meets this criteria, and it can't be absorbed or metabolized. And the rate that we have that at is 125 milliliters per minute of plasma cleared. And this is a really important number when you compare it to some of the things that can go wrong. So I have these examples of different values that we need to compare to that 125. So the first one, A, is 5 milliliters per minute and that if it's lower than the 125, you know that that's being absorbed, it's being reuptaken. And then B is 151 milliliters per minute, and since that's larger than 125, you know that's being secreted, it's being made. And then C is 50, and that's still below, but higher than the 5, so it's being absorbed about half. D is 0, and so the whole thing was reuptaken. It's completely absorbed. And then 130 milliliters per minute is just a little bit of secretion. And this E is creatine, and creatine meets the assumed criteria. Increase in P creatine is you know that you've got a kidney problem, and that's also going to lead to decreased U creatine. So renal blood flow is how quickly blood is filtered through. So we've got clearance, which is how quickly can I clear out the solute, and then renal blood flow, how quickly blood is filtered through. So we've got this graph, and on this side we have urine concentration, and then we have plasma concentration. And we've got our renal threshold, and then we've got our saturation point down here on our other end, which is also kind of a renal threshold. And then in the middle, we have our GFR, glomerular filtration rate, and this is generally creatine or inulin. And then this line that we've drawn in between them is our secretory protein saturation. And this kind of describes everything that's going on. And this pink line is our glucose, which we want to be 100% reabsorbed, or like we talked about earlier, if it's not, we know that we've got diabetes. And so these all work together to create and maintain this homeostasis within our kidneys. So it's super important with the pressures, because if you start changing these pressures up, you're going to cause vasoconstriction or dilation of the arterioles and blood supply around this, which is going to impact the filtration rate, and then all of the rest of this gets affected. So, okay, next video, here we go. Okay, let's continue with the kidneys. So we have two different feedback systems. We have the myogenic and we have the tubuloglomerular feedback system. The myogenic is what increases blood pressure. It's intrinsic to smooth muscle, and it's direct activated by calcium channels. Tubular feedback decreases blood pressure, decreases sodium chloride. And this impacts our macula densa that we've talked so much about. And the macula densa is what controls the nitric oxide, which is what controls vasodilation. And if you have vasodilation, that leads to increased GFR. So, in relation to this, if renin enters at the macula, it helps with the decreased BP. So it'll increase that BP. So in order to understand a lot of this, we have diuresis and antidiuresis, and we have different levels. So as our solution is coming through the glomerulus, it comes down and we start at the level of 300, and where these blue lines are marked out, that means it's water permeable. So you have solutes on the outside that are dragging out the water, because water always goes to the solutes. So the osmolarity at these levels is how high it is, making it that same osmolarity in there. So if you have 300 that comes down, it's going to want to become 400 to match that, and it goes through each step, dragging out more and more water. Then as you come up through here, it's no longer water permeable, but you do have different channels that will re-establish the gradients. And then whatever's left, you are losing forever. You're gonna pee it out. So for diuresis, that means we have very high volume, low osmolarity. So not as much as being absorbed at the end, but you have a large volume. Antidiuresis is a little different. It's high osmolarity, low volume. So the only difference here is that not only is this water permeable, but then you've got water permeability on this other side as well. So you're sucking out a lot more water in that process. And then down here, we kind of have the same thing, except this is our juxtamedullary that you see right here. And then this is the collecting duct. And this is showing our urea permeability. So up top, you don't have any urea permeability. It's only at the bottom of the juxtamedullary loop of Henle and at the bottom of the collecting tubule. And so as you can see, that's permeable to sodium chloride and our urea. And the further down you go, the more permeable it is and the more concentrated your urea is going to be. Okay, so we got to talk about some important hormones that are going on here. So we've got these different receptors by the glomerulus, and ADH, or the antidiuretic hormone, is what stimulates this. And this goes to the osmolar receptors, and that's set at about 300, and our net equilibrium is 310. And so this comes down, and we've got our arterial that's influencing and affecting the osmolarity of our osmolar receptor. And then you have an excitatory, or an EPSP, that then stimulates. It's right here, and baroreceptors can also influence that. So increased stretch is going to lead to a reduction, and decreased stretch is going to lead to an increase in ADH. And then we have a G protein here, and angiotensinogen 2 comes and binds to that. And then we also have the increase in ADH over here. Is after all this process has taken place, that's what it leads to. And that responds to the osmolarity that we just talked about. So we've got angiotensinogen plus renin is going to lead and create angiotensin 1. And then angiotensin 1 plus ACE leads to angiotensin 2, which is what we had up here. So angiotensin 2 does 4 things. It goes to the brain, which will increase ADH. It's going to increase thirst. It's going to increase your craving of salt. It's going to go to the brain, which then constricts the efferent arterioles. And then it's also going to go to the adrenal gland, which is going to stimulate aldosterone, which is then going to increase your salt. And then we have it coming over, and you're going to have system-wide vasoconstriction, which is going to lead to an increase in blood pressure. And this is going to then, we're going to have a lower BP, which is then going to lead to a low GFR that we talked about earlier. And that low GFR is going to then stimulate the angiotensin plus renin. So there's another feedback cycle. And then angiotensin 1 also is going to create ACE2 inhibitor. And this leads to angiotensinogen 1 through 7, and this lowers BP. And we learned during COVID-19 that COVID-19 destroys ACE2 inhibitor, which can be a pretty serious problem. So there is the end of the kidneys. And we're on to the lungs. So lungs are elastic and they are designed to collapse. So we've got 4 different things that we need to know about the lungs. We need to know how air gets in and out. We need to know how do you exchange it, or exchange the O2 and CO2. How do you transport that O2 and CO2? And how do you regulate it? So a lot of that can be determined by the law of Laplace, which is P, standing for pressure, equals 2 times the tension over the radius. If you increase P, then you're going to decrease your radius. If you decrease P, you're going to increase your radius. They're inverse of each other. So here we have some alveoli, and alveoli are the 2 of them together, and then alveolus is singular. And one is smaller than the other. And when you have a smaller radius, the pressure decreases. So when you inhale and air comes into this, if you've got air in here and air in here, you would expect that they would equalize each other out, but that's not so. Because this is more of a negative pressure, the air goes to where there is the negative pressure. So this one is going to collapse more. So what can we do to overcome that? We're going to get to that in just a second. So first of all, we kind of need to know a little bit about our atmosphere in the world. So this is our world and all of the sea level, and we have mountains and different levels of atmosphere. And so we start at 640, and inside our atmosphere we have O2, CO2, and nitrogen, and this is our atmosphere, and that's going to impact the air that we breathe. So when we were talking about our scenario a second ago about why air goes to negative spaces, but yet our alveoli don't collapse, this is how we explain that. So in order to understand that, we have to understand surface tension. And we have surfactant in our lungs, and surfactant removes the tension. It's kind of like a soapy substance, and it lines our lungs. So we have our surfactant shown in the black, outlining the space, allowing movement. However, on this side, we're going to need more surfactant because it's such a smaller area. So to counteract the space difference, or how big the difference is, it counteracts by creating more surfactant for that area, so you have the same amount of surfactant per surface area. This, like the little cells that make this up, are called pneumocytes, type 2 pneumocytes, and these are what make the surfactant. An O2 depletion, which would happen if this is to start shrinking, if you're not getting enough oxygen because it's all going to the negative space, that O2 depletion is going to create cortisol, which then comes in and creates those pneumocyte type 2, which makes surfactants. That's how it overcomes that problem. Now, pneumonia is a big problem because that increases the water in your lungs, which then reduces the surface area and it keeps it open. So it's less negative and it's hard to get oxygen in. Okie dokie. So now we need to talk about this system. So CO2 plus H2O, when you put energy in, it turns into CH2O plus O2. And that kicks energy out as well the other direction. So total pressure equals sea level. Now, we need to refer back to Boyle's law. When you have a bigger space and all these particles bouncing around in there, your pressure is going to decrease. When you have the same amount of particles, but you decrease that space, that's going to increase your pressure. And we are negative pressure air ventilators. So these are our lungs, and we have our diaphragm. This is our pleural space, and that's going to be -5, and that gets more during inspiration. That increases during inspiration. These dotted lines, that's our ribs, and then our diaphragms attached to our lungs, and then this creates a suction cup effect to the rib cage, pulling that pleural space and pulling all of those membranes out, which then is going to increase the space available. And since we've increased that space, we've decreased the pressure, and we've increased that negative pressure, and so air flows in, and then we exhale, pushing all that out, making the space smaller, and the air goes out. So we are going to jump down here to our pressure volume loops. Now this is normal inspiration and then expiration, and this side is volume and pressure. When you increase the volume and decrease the pressure, you're going to get this pink line right here, which means you have lots of compliance. And this is smokers' lungs, so it's hard for them to get air out because you've increased their volume, but they can't push it back out very well. And that can be caused by the surfactant isn't working as well because you've gunked it all up with all this junk from smoking. The other hand is you've got lots of elastance. And this is restrictive lung disease. So this is hard to get air in. So this is with premature babies. They don't have surfactant and enough surfactant made. And so it's not very elastic, and they can't get these open like we had up here. So we have two equations. It's elastance or pressure. Is E equals the change in pressure over the change in volume. And then we have compliance, which is volume, which is C equals change in volume over change in pressure. So the more volume, the more compliant, and the less volume, the less compliant. So we need to also know how the blood factors into all of this. So we've got an alveoli and then our vessel. And then we've got, that's in the lung. And then in the tissue, we've got our cells, and then we've got our vessel. So first of all, we start with a PaCO2 of 40. And then we've got our O2. So the O2 diffuses into the plasma of our vessel, and then we've got all these red blood cells in there. And inside the red blood cells, we have hemoglobin. And this hemoglobin, we're going to jump over here really quick to describe what's going on with hemoglobin. Hemoglobin is made up of these 4 different iron groupings. So we have alpha 1, beta 2, alpha 2. And inside that space is 23 BP, which pulls them all to the T state. So up here we have, if heme is in the T state, then it means it's deoxygenated, and then the R state is oxygenated. And this is going to influence if we have CO2 or H2O, which I guess, well, yeah, we'll describe that. So first of all, let's start here. So we have our oxygen that comes in and it becomes binded to the hemoglobin. Now we also, that is going to kick off our chloride. The chloride is coming out. And then we have bicarb, HCO3, that comes into the cell. And when that comes into the cell, it's going to break up. And that hydrogen is going to come and bind to that hemoglobin. And that is what the carbon dioxide plus the hydrogen is going to turn to H2O, and CO2. So that H2O, we know obviously water. And then we've got our CO2, which then is going to leave the red blood cell and come out into the plasma, and part of it's going to stay in the plasma and part of it's going to come back up. Now these numbers of 40 and then this will be assigned a number, these have to be equal at all times, and if they're not, then some of this, the plasma CO2 or the PV CO2, which in our scenario is 45, because that's higher, you're going to have to take some of that and push it back up to here. And what that does is that means you're exhaling your CO2. So here are some numbers that we need to know. So 73% of CO2 is associated with this bicarb, this HCO3. 7% is in the plasma, and then 23% of CO2 is attached to the hemoglobin. So CO2 pops off when O2 attaches, so it's one or the other is attached to the hemoglobin. Now for tissues, you have oxygen. You want to oxygenate the tissues, and that's going to come from the red blood cell that started up here. So you oxygenated your red blood cells, and they travel and they get here and they kick off that oxygen to go into the tissues. And then it's going to convert to CO2, and that comes back into the cell, and then we still have that binding to the hemoglobin. The CO2 is then going to become the HCO3, and that is going to leave the red blood cell. And you still have that plasma CO2 that you've got. And that's 7% worth. So next we need to know a little bit about glycolysis. So we start with a 6-carbon chain, and that gets popped off and becomes 1,3-biphosphate. Now, something cool is that when this becomes activated, it's not going to be stable and it's going to push things apart. And this is our 2,3 biphosphate, or 2,3-BPG. And that's created by your red blood cells, interestingly enough. So fetuses don't have the B1 chain, and they don't bind that 2,3-BPG. So in order for them to have that, it has to be made by the placenta. And so we're going to kind of describe a little bit more of that with our oxyhemoglobin saturation curve that we have right here. So on this side we have percent saturation, and then down below we have PaO2. And so this is, the pink is the normal, and then it can either left shift, which means you're becoming more right state, or R state, and then you have your right shift, which is that red, and that means it's more in the T state. So this can also be caused from heat. And then this is significant of where we have our 40. That's where that starts to make a difference, and that 75 they connect. And so there is our first lung video, and we will continue to learn about that in the last video. Okay, last but not least, we're going to hurry and run over some more stuff to do with the respiratory system. So we're going to start with Henry's law, and that states that CO2 is more soluble in water than O2. So how does this affect us? Let's go over this. So we've got our alveoli. We have 160 coming in, and it's diluted with water, bringing it to 149. And the partial pressure in the alveoli, the PaO2, is 102, and we have all this exchange going on between the PvCO2 and our PaO2. And so that's going to bring our PaO2 down here to 40, and our Pa 102 still right there. And then our O2 is going, or we're having our oxygen come into our cells, like we talked about previously, and that's our PaO2 is 40. So the equation to describe this is PaO2 equals 21% of the pressure in the atmosphere minus the pressure of H2O minus the pulmonary artery, or the pressure, blah, 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 the pulmonary arterial CO2 divided by the R, which is CO2 divided by O2, and the standard for that is 0.85. So we got 0.1 times the average is 760 minus 50 gives us 149, and FiO2 is that 0.21. So a few more things that we need to know is TV is tidal volume times breaths per minute, and AV, which is the alveolar ventilation, is our tidal volume minus DS, which is our dead space, times our breaths per minute. And that dead space is the air that just keeps getting recycled and recycled and recycled and just doesn't make its way out, and keeps getting sucked back in. So V is the air that reaches the alveolar per minute, and Q is the blood that reaches the alveoli per minute. So we do the equation of V divided by Q, and when we're done with that, we get 1 liter of air equals 200 milliliters of oxygen, and then 1 liter of blood gives you 200 milliliters of oxygen. So that's kind of our constant. We're going to talk about COPD really quickly. COPD is chronic obstructive pulmonary disease, and that is quite close to emphysema. So what happens is they have a hard time expiring or getting the air out. And with emphysema, your alveoli become fused, increasing the volume and the space in your alveoli. But there's still the same number of capillaries, so you're not as able to, I guess, get as much oxygen out of that, and the air becomes trapped because you haven't increased your surfactant and the elasticity to be able to push it back out. So that can be quite dangerous. Thank you, and we will see you next time.